The next few flavors of interventions, right? So this is called an intervention because you're intervening in the network, right? Intervening in the process, manipulating the network or the virus or something like that to prevent the spread of the disease as much as possible. So the other thing is data aware versions, right? Which is immunization or intervention after you know the epidemic has already started. For example, in many cases you don't expect an epidemic and the epidemic has already happened and many people are already infected. Now the question becomes, how do you take a decision of where to intervene and how to intervene in this situation, right? So this is called data aware problem, right? So the data aware vaccination problem. So the idea is that the problem is given a graph and some infected nodes, right? And the infected nodes can be given as an uncertain distribution as well, right? You can say that, okay, I roughly think that this part of the country is infected, this county is infected, this district is infected, and this part of the city is infected, that part of the city is less infected, and so on, right? So you can even give an uncertain distribution. For sake of simplicity, I am assuming here you're given exactly which nodes are infected. And how do you distribute K vaccines? Again, how do you pick the nodes to remove so that you get the maximum benefit? So to minimize the expected number of infected nodes at the end of the epidemic, right? So sorry, right. Suppose you know that these two nodes are infected in this graph. You have one vaccine to give. Whom do you give that vaccine, right? Right. Whom do you give that vaccine? Any idea? So if you remove A, you will save A and D, right? That's it. If you remove A, you will save A and D, no one else. If you remove B, you will save only B, right? Because this guy can get infected through A anyway, right? And this guy can get infected through C anyway, right? If you remove C, you only save C again, right? So the best solution clearly in this situation is that you remove A, right? Because then you can save at least that part of the graph, right? So that's what you want to do it efficiently in a scalable manner. How do you pick these nodes very quickly? So the complexity of this problem is, of course, it's nphard. You can reduce it from maximum K intersection problem. So I'm not going to detail. It's not submodular, unfortunately. So you cannot get a very trivial greedy algorithm here. So it needs a little bit more. It's a bit more challenging, and actually you can even prove that DAV is hard to approximate within an absolute error. So all of these things hold true. So what is our approach, right? So you can still attack this problem in this way. So let's simplify. So first thing, which is a very trivial trick, is that you can merge all the infected nodes into one node, right? So you can merge all the infected nodes into a single super infected node, let's call it, right? So it tells you, so these two nodes can be really thought of one node which connects to all the other neighbors, right? So this node will connect to A as well as B as well as C. So not a big deal. So you can prove that these two are equivalent, right? It's like a logical OR. Okay, the second main idea, so you can get an optimal algorithm in trees. If the graph is a tree, you can get an optimal algorithm. What does that look like? So we call the algorithm Dawa, which also incidentally means medicine in Hindi and Urdu. So because the data aware vaccination problem. It says select nodes with largest benefit, right? So what does that mean? It means, suppose this is the expected number of saved nodes after removing set S on graph G, right? So this is what you want to estimate, the expected number of saved nodes after you remove the set S on graph G, given such a distribution of infected nodes. The benefit of adding a node J into S is roughly this, right? Gamma, which is sigma prime, which is if I add J to set S, how many nodes I save, minus how many nodes I would have saved if J was not there, right? So this is the gain, the marginal benefit of adding J. So this is the number of saved nodes after adding J to S, and this is just this, right? So this is basically saying the additional number of saved nodes when I add J to S, right? The additional number of nodes I can save. So the idea mainly is that if the graph is a tree, then you can do this optimally. You can pick the next node which saves this much, and you can prove that this is optimal, right? So the benefit of this node is 4, the benefit of this node is 5, right? So if I remove 4, you can see that I'll save everybody here, right? Because it's a tree, remember? If I remove 4, there is no way the infection can reach from I to these nodes, right? There is no way this can reach. So hence, effectively, if I cut off this node, then this whole region is saved, right? That's the main idea. So you can do this optimally for trees, right? So you can prove for any set S, the chosen nodes in the optimal set must be in the neighbors of the infected node. So must be at this level. Again, these are lemmas I'm not going to prove here. The second benefit is that the second fact is that the benefit of each such node is independent of the rest of the set S. That's also a very important fact, right? The benefit of each node is independent of what else has been chosen in set S. Hence, the problem really becomes very trivial, right? Because then you just need to estimate, look at the neighbors of the infected node, remember I only have one infected node now, right, because I merged all the infected nodes into one. I have only one infected node, I can calculate the benefit of each node independently, and I just need to add them quickly to the set. So it's a very simple algorithm because of these two lemmas, and you can prove that this is optimal, right? Okay. So the Dawa tree algorithm is very trivial. Select top k nodes from i's neighbors with the maximum benefit, right? And you can do this in linear time. So just a walk over the graph. So how do you extend this to arbitrary graphs? That's the question, right? So we know that for arbitrary graphs it is nphard, right? So what structure can you extract so that at least you can get some decent solution from it, right? So the idea we have is that we have the optimal algorithm for a tree. So the best thing we know is extract a tree, right? Extract some spanning tree from the graph and then run Dawa tree on the spanning tree, right? So suppose what kind of tree, right? So an obvious answer for computer scientists at least is a minimum spanning tree, right? That's one of the basic algorithms we study. So suppose we extracted a minimum spanning tree from this graph, right? So this is a general graph. Why is this a general graph? Because you have two edges here, right? So this is not a tree, just to point that out. It is not a tree. So suppose I extracted an MST out of this, right? The optimal solution here clearly is this 4, again, because if you remove 4, I save 5 nodes immediately, right? Whereas in the MST, if you find this, the optimal on MST by Dawa tree will be something like this, 2, right? Because MST is kind of saying that if you remove 2, you will save everything below it. But that's precisely what is not true. So that gives the intuition that you probably need another algorithm for this, right, or another tree for this. You need to extract the right tree from this graph. So what is this tree, right? So our solution is that you don't extract the minimum spanning tree, instead extract what is called the dominator tree, right? So this is a very well-known tree in software engineering to study data flows, right? So the idea is that you take this graph and extract the dominator tree, which means that you extract this u dominates v relations, which says that if I remove u, I'll definitely save v. That's the main idea, right? If I remove a node u, I can definitely save node v from getting infected. That's the kind of relation you want to capture from the graph. So every path from I to v contains u. That's the intuitive meaning of this tree, right? So if there is an edge u to v, that means that every path from I to v contains u, right? So if I remove u, I'll save v, obvious. Now, so this is called the dominator tree, right? So u is an immediate dominator of v, that means u dominates v and every other dominator of v dominates u, right? So using these relations, you can build a dominator tree. So suppose this is the merged graph, you can build the dominator tree something like this. So this is the dominator tree of this graph. So this is a very useful concept which we'll see later in on other applications as well, right? So this says that if I remove 4, I'll definitely save all of them. But see that if I remove 2, I can only definitely save 5. That's it, right? So this captures the more relevant information which you need for this vaccination, right? So the optimal solution on the merged graph is still 4, and the optimal from Dawa tree on this tree is again 4, right? So the nice thing is that this can be built in linear time. A very nice paper by Boschbaum and Tarjan way back in '98. So which shows that you can build this dominator tree in linear time, near linear time from the merged graph, right? So which is what we want in a scalable algorithm. And you can prove 2 facts. The optimal solution should be among the children of node I in the dominator tree. So this is a strong statement, right? The optimal solution on the merged graph should be among the children of the root I in the dominator tree, right? So you can prove this relation for any arbitrary graph. And fact 2, for some special cases, running Dawa tree on the dominator tree itself gives the optimal solution. So you can prove both these things. So that gives you more confidence in running and doing this algorithm, right? And as I said, it's already linear time, so it's a very nice thing. How do you weight the dominator tree is a different question, so we won't go into detail there. Weighting the dominator tree is sharply complete, you can prove that. So our solution, we adopt a heuristic which says that, okay, calculate the shortest paths or the maximum propagation path probability from I to V using Dijkstra's algorithm. So again, these are details. So what is the big picture? Our Dawa algorithm is not that hard to get. It's basically build a dominator tree from the graph, weight it, run Dawa tree on T with budget is equal to 1, remove V, iteratively you will go on till you get set K, right? So this is the merged graph, you get the dominator tree, the first node is this, then you remove the second node and so on and so forth, right? This is the merged graph, you again set this, iteration number 1, right? So then the iteration number 2 will select the next node. So the nice thing is this is Ke plus V log V. So it is not linear, but it's still subquadratic. So it is still pretty scalable for your given situation. but it's too slow for very large networks, right? So what do you do that? So there you say that don't build the dominator tree after every removal. That's it, right? You build a dominator tree once, run Dawa tree on T with budget K, and that's it, right? In practice, we found that the performance of Dawa fast is very close to Dawa, right? And the time complexity becomes even faster, right? V log V plus K. So here you had K times V log V, right? So now it becomes just V log V. Okay, cool. So experiments quality, again, these are some baseline algorithms. So we also have preemptive algorithms like NetShield here. You can see that, if you can see, apologies for the short font. So you can see the total number of vaccines, and this is the higher is better, right? This is the expected number of healthy nodes. So you want to maximize the number of healthy nodes remaining at the end, and you can see that we are very close, and you can also see Dawa and Dawa fast are very, very, very close. And in fact, for very large networks, you cannot even run Dawa because it is so slow, but Dawa fast gives you a very good algorithm, right? So more results are in the paper. As I said, you can extend this to noisy data as well, so uncertain and noisy initial data. For example, you may not really know all the infected cases in the graph with pinpoint accuracy, but as long as you can give me a rough distribution and uncertain distribution of where the infected cases are in the network, I can still do a robust algorithm, which is still subquadratic, right? And you can also do convert this to an online setting. So there was a paper recently in CIKM which does that, right, which converts this problem into an online setting. Suppose I want to choose the next best node in an online setting, then how do I do that? And the data is changing at every time, like in a streaming fashion. Okay, so data aware. So this was remember, this was data on a cascade style models, right? But you can also study this thing for linear threshold models. These are threshold models which try to model behaviors which flip due to thresholds, right? For example, I will buy an iPhone if 5 of my friends have bought an iPhone. So it's a very specific threshold model, right? So that's not really an independent probability model, right? So if 5 of my friends or 6 of my friends have an iPhone, they try to infect me with probability beta. That's the kind of models we have studied before. But you can extend this to linear threshold models also. So there was a nice paper last year, 2 years back in KDD, which tried to does the data aware problem for linear threshold model, right? So they proved that for edge deletion, this marginal gain, right? So remember, for this marginal gain is not submodular or supermodular in the cascade style model case, right? Where you have probabilities. Once you have specific thresholds, then this model becomes supermodular. So the problem becomes easier here, right? Because it's supermodular, you can clearly minimization of supermodular is nphard, but again, the greedy algorithm is near optimal. So this is just the flip case of maximizing submodular functions, right? So hence you can get a very efficient algorithm there. So the main thing is to prove that this is supermodular. Okay, good. So hopefully I've given you some flavors of different algorithms, and the final one is group-based algorithm, right? Where you have allocation based on groups. So what's the motivation for that? Sometimes individual immunization cannot be easily turned into implementable policies, right? So for example, if I tell CDC you need to immunize person number 131 living in San Francisco, that's not really realistic for, especially for things like flu, right? So there they might say, okay, let's roughly immunize this part, give 100,000 vaccines to this area of San Francisco and distribute it randomly in that area, right? So that's what they can do. So what we want to say here is that, okay, how do you, under this setting, how do you distribute vaccines so that the epidemic gets stopped as fast as possible, right? And this can also be the reason because it's very hard to ensure the specific individuals take adequate vaccine, right? So it's very hard to ensure that every person which you have chosen takes the vaccine, right? So you want to do it in a roughly uncertain and distributed fashion. So we had this paper in ICDM last year which tries to study this problem. And the observation also is that groups naturally exist in many underlying networks, right? So people can be grouped by ages, demographics, occupations, the place they stay, and so on and so forth, right? And each of these groups can be utilized when you are spreading vaccines, right? So friends group by the same interests, geolocations, and so on and so forth, right? And the groups need not be based just on linked communities. So this is an important point, right? It's not necessary that people you come in contact to are your groups, right? You make, like for example, you can say all KDD attendees are a group, but it's not necessary that KDD attendees are friends, right? So they may not be link-based communities, but they may be groups based on some certain other attributes. And that's the main point. In this paper, we wanted to make sure that you study this more general problem where the groups can be based on anything, any attribute, any feature value. So it's also more feasible and more practical in this. So here we study how do you select groups to control propagation over networks, right? So the main idea here is that you simulate the distribution process in real life, right? So the decision maker has a bunch of vaccines. It gives the vaccines to different groups, right? And the groups randomly distribute vaccines among its members, right? So this mimics most of what happens in real life. CDC will give 1,000 vaccines to, say, Virginia Tech. Virginia Tech will hold a clinic which will say that all students and faculty are welcome to get their shot. People will randomly self-select themselves to come and go there depending on their time schedule or whatever they are trying to do. Hence, we can roughly model it as a random process within each group, right? But how many vaccines should Virginia Tech get is a decision which CDC needs to make. And it can make this depending on the contact network of each city, right? So the idea is distribute vaccines to groups, randomly vaccinate or quarantine whatever within each group, right? Under this setting, so we had a bunch of scalable algorithms. For the edge model, edge node deletion under the linear threshold model, we can get again a 1 minus 1 minus approximation. With the node under the spectral radius where you want to distribute the vaccines to lower the spectral radius as fast as possible, you can get a constant factor. For the spectral radius, again, you can get a much faster. This is very slow, right? It's v to the power, I think, 4, right? So you can get n to the power 4, where n is the number of groups, not the number of nodes in the graph. This is really slow, but this is very fast. Then the edge spectral radius, again, you can get an n to the power 4. So you can get a variety of these algorithms, provable approximation guarantee algorithms for a variety of cases. So here's an interesting case study, right? So what we did was we took the Portland graph, distributed vaccines based on the groups present in the Portland graph, and you can see that our observation is that our methods choose elder people to distribute vaccines to, right? In contrast, typical, state of the art other methods tend to uniformly distribute vaccines. So this gives a suggestion the results match the current CDC practice that it targets vulnerable people, right? So roughly, intuitively, it tries to target vulnerable people, but you can now have a very strong justification which can change depending on how the contact networks change of which people you should target to, right? You should not distribute vaccines uniformly. You should pick groups of people which are more vulnerable in some sense from a contact network setting. So we are making it precise in this setting, right? Okay, good. So Naren, how much time do you have? So when should I give it? 2:35, right? Yeah, a few more. Okay, good. So good. So this kind of ends the immunization part, right? So we have seen preemptive immunizations where the disease has not started, but you want to preemptively immunize as much as possible in the best way possible. We have seen data-aware versions, and we have seen group-based versions. In all of these settings, the analysis which did in the first part was very crucial, right? What should you minimize? Right? That question can be answered only by the previous analysis. But how should you do it and how scalably you should do it is a different question, right? That's what we are trying to answer here. And we have seen that methods based on submodularity, then dominator trees. So very unexpected techniques are useful here.
If it's biased towards older people, why not bins 9 and 10? It's just bin 8 or bin 7.
Good question. So here, these are too old in some sense, and they are not very well connected in the network. So that, sure. So that's the point. You don't want to blindly say that's the danger with rules of thumb, which you just say that okay, immunize young people, immunize old people, because they are always someone younger than you, right? You need to immunize the correct old people, right, at the right age. And what we are saying is from the contact network, this is the right age for immunization at that point. Yes, babies are also important. So you see that we have some more things, but elder people are more important in vaccine distribution. So babies are immunized for a different reason because we don't want them to get sick because of the other reasons. Right, sure. So they are here, right? But they are not as much as elder people. So if you want to prevent the spread of an epidemic, the main pinpoints are elder people because they come in contact with babies, they come in contact with middle-aged, young people, and all of them. So they are very important there. So this is an interesting result because a lot of studies have also tried to say that, recent studies in Science and Nature have also tried to say that how should you target these groups based on their contact patterns, right? And the contact patterns have been available only now. So that's why this is an interesting current problem. Any other questions before I move on to other algorithmic problems? Expected case, yeah.
Well, not expected, right? You wanted to maximize in the worst case, you wanted to immunize parts of the graph in case the rest of the graph gets
Oh no, we were. So the problem here is to immunize. So here, let me go back, right? A good question. So right. So what we want to maximize is the expected number of saved nodes. So it's still the expected. We still want to maximize the expected number of saved nodes. Yeah, I might have given you the impression that I was looking at the worst case because of the trees and the graphs I have made, right? But you can calculate this expected number, and that's why this is not a trivial question. How do you weight the Dominator tree, right? Because you still, this weighting is what gives you the expected. So at each probability, you want the probability of infecting the next guy, not just the. A very good question. So the maximum eigenvalue question does not come here because the maximum eigenvalue is when there is no disease on the network, right? If I tell you that the disease has spread, I mean, it does not matter if there is an epidemic or not, right? If I know that the disease is in that corner, I will try to vaccinate that corner, right? That's the point. So there is no meaning to spectral radius because even though there might not be an epidemic, you still want to prevent that epidemic from happening as much as possible in that corner, right? So given the initial set, the scenario changes, the calculus changes, right? Now you don't care about epidemic or no epidemic, you want to prevent the epidemic as much, infection wherever it is, right? So that's why it's a different thing. Yeah. Good question. Any others? Okay, so yeah, so this is the immunization type of problems, right? So I'll go over a couple more before I give it to Naren for the rest of it. So how do you reverse engineer epidemics, right? So this is another interesting problem which might be useful in many different settings. So what's the problem definition? Very simply put, so suppose you have this graph, right? So this is a grid graph, right? It's a grid graph. Every node is connected to the north, south, east, west of its neighbor. And you have a 2D grid, plus seems infected, and so what you really want to ask is who started it, right? So suppose you are a detective, you come to a carpet and you have see a wine spill, right? And you want to say that, okay, where the wine spill might have started from. So if I give you these two blobs, intuitively you see that this might be the two starting points of that epidemic, right? So if these are all infected people, it's easy to say that, okay, maybe these two people started it because it seems uniform, symmetrical, and so on and so forth. So the question is, how do you do this algorithmically, automatically, right? Because it seems intuitive when you look at it, but how do you formalize this problem and do it algorithmically, right? So there have been, it's not been studied much, but there have been two nice papers in 2010-11, which are kind of looked at very specific, if you give me the budget, if I tell you how many starting points are there, or very specific graphs like deregular trees and so on. So the question was, can you generalize this and give a more scalable algorithm, right? So we had the two-part solution for this, right? So we said that, okay, let's use MDL, which is the minimum description length principle, for the number of seeds. So think of it as a model selection principle, right, which tells you that, okay, how many seeds should have been here? If I give you this blob, I mean, a single seed seems unlikely, right? Why? Because to describe this data set, a single seed will lead to a lot of code length. That's the main idea, right? Whereas if I use two seeds, then I can get a smaller code, right? So that's the main idea of minimum description length. So it's based on Occam's razor, right? The simplest explanation is probably the best explanation. So so I'll not go into detail here, but the main point is that you can get a linear time running algorithm in nodes and edges, which we call NetSleuth, which can tell you immediately which might have been the node starting points given a snapshot of infected nodes, right? So the main idea we have based this on called exoneration, right? So suppose I give you this chain and I tell you that these three nodes are infected. What might have been the starting point? What might be the first node to get infected? The blue one, right? Sounds reasonable. Why? If I chose this node to get infected, then why did this node not get infected, right? That's unlikely. Why did its neighbor not get infected till the next three nodes got infected, right? So what you are really calculating is an MLE estimator for what is the starting point in rough sense. What's the most likely estimator, most likely starting points for a given set of infections all over the network. So now, if I immediately put some uninfected nodes, right? So it's the same infected subgraph. These three nodes are infected. But now you have a bunch of uninfected nodes. Now which might have been the starting points? The two blue nodes. It's unlikely that the central node would have been the starting point because why didn't these nodes get infected then, right? It's a lot of code length or bits to spend to explain why these nodes didn't get infected, right? It's less likely. So what's the main point? That the likelihood of any node to be the starting point depends on the distribution of where the infected nodes are, but it also depends on where the uninfected nodes are, right? So uninfected nodes around you make you less likely to be the starting point, right? And infected nodes around you make you be more likely to be the starting point. So that's the main idea. You can use this idea to build a pretty scalable and efficient algorithm. So here's one example which I show here. So this was, remember, the CDC graph from 2007, the 35 tuberculosis patients. As I said, intuitively, if I just look at the graph, it's pretty obvious that this might have been the patient 0. So technically in public health, this is called patient 0, right? Who might have been the starting point. So they get this through contact tracing. But you can apply our algorithm and you can get exactly the same node pretty efficiently. So the patient. Yes, so cluster centroid will, this is not really the cluster centroid. So in the grid case, it might look like that, right? Because these are clusters in some sense, right? But in real life, these infected subgraphs may not be nicely D-lined like this. So if you find the cluster centroid, it will not be close enough to this. And you're assuming cluster centroid in the understanding that the graph is a grid graph, that there is equal, the spread of disease is very constant as you go away from the cluster centroid, right? But in real life, that may not be the case. For example, in this snapshot, this has a high degree. So this node is connected to a lot of people, but these nodes are not connected to that many people, right? So if you take the cluster centroid here, it may lie somewhere here, not here. So that's the main idea. But yes, that's what you want to kind of formalize and capture using these things. And many extensions since, after there have been many extensions, so they have been extended to different models, right? So right now SIS, SI, so our paper was based on SI models, but you can now extend to different models. Temporal networks, right? So this was an ICDM where the network is varying. And we also actually have a paper in this year's KDD, which is on noisy input. Suppose I don't know exactly who is infected, but I sort of know who is infected, then can I robustly infer who started it? And also more rigorous results on specific graphs, right? So for example, if the graph is a expander, a graph is a deregular graph, then you can get more specific rigorous results, right? But our focus was more on scalable algorithms for arbitrary networks, yeah. So we can do that, but for simplicity, I just assume that the parameter is given. Let's say the beta is given. Even then, the problem is very hard. But you can infer that too. Right. So I'll give you a simple example. If beta is 1, that means it is certain that your neighbors get infected. Then the problem becomes very different, right? Because then it depends on your expansion, right? How many neighbors you encounter at each step. So it still depends on that if the beta is not 1, but in a different way. So yeah, fundamentally, for a given model, change of beta will change the answer, but not maybe the technique of solving the problem. But a different model might need a different technique. Yeah, so in the example I gave you, not. But that's what I wanted to say, that people have tried to extend that kind of analysis to, okay, now if you have timestamp information, and the paper we have in this year's KDD deals with that. That suppose you have timestamp information of when each one got infected, then how do you use that? Right, but the point is that timestamps are not very granular. It's not as if I know to the nanosecond. I just know probably this week somebody got infected, right? And that also may be uncertain, because when you get infected and when you actually report the infection may not happen at the same time, right? So there's a lot of uncertainty there. Okay, so very quickly, and I'll okay. Okay. It was a sign that I need to stop talking. Okay, so the last algorithm before I turn over the thing to Naren. Right, so this is the reverse engineering epidemic problem, right? So now another algorithmic problem which we can study is how to estimate influence graphs, right? So this is also a very fertile area of research which has seen a lot of different papers recently. So what's the problem statement? So this was the paper by Gomez, Rodriguez et al. In KDD 2010. So the idea is that you are given different snapshot of cascades, right? So you are given cascade CI, which goes like this, cascade C2, which is probably like this, and so on. You don't know the real network. You are just given these cascades, which are snapshots of what is happening, and the true network is probably this, right? And you want to infer that from this log, right? So this is the learned network from this set of cascades that says that A1 came, so A1, the node A1 was infected by C1. That means the C1 item came to A1 at T1. So you have these triplets, right? You want to learn the true network, and you want to see that the true network should, you want to make sure that the learned network is as close to the true network as possible, right? So a very natural problem. So more specifically, the problem statement is given a set of cascades, infer the static hidden directed propagation network G plus, right? So the trace of each cascade is represented by the triplet, like node, which got hit by which cascade, which is like which virus, at what time, that's it, right? And you can have set of features for each node or contagion, right? This is a flu, or this is hashtag beaver, or hashtag Olympics, or hashtag whatever, right? And you can have a, so let's call these three probabilities, right? Which is probability of C, the probability cascade C propagated in pattern T. This is probability of C given G, which is probability cascade C occurs in G, and this is probability cascades, a set of cascades C occur in G, right? So what the problem is, get the MLE estimator, which is the maximum likelihood estimator, G star, which maximizes P, that the probability this set happens in G, that's it, right? So very natural problem. So the main idea of the netinf algorithm by those authors was that the original formulation can be written like this: the G star is the G cap is the estimator, which maximizes this probability, but this probability is a product of multiple probabilities, right? And this is intractable. The alternative formulation they give is to say that this probability, let's rewrite this as another formulation where you calculate the maximum tree, the tree which maximizes the probability for each cascade, right? And then take the product. So that, if you write it like this, then the objective function actually turns out to be submodular, which is very nice. Now, because it is submodular, you can near efficiently solve it, right? And then you can get the best tree. Given each cascade, you can compute the next best tree in a very linear online fashion. So they ran this learning algorithm on a set of block data set, the meme tracker, which is pretty popular and a famous data set, which say, and they found something like this. The graph they learned shows that the most of the diffusion is from media to blocks, which was kind of interesting, right? Because you would have assumed that media trying to picks up things which are in the blogs, right? But they were able to find that in their data set, at least, most of the influence happens the other way around. Most of the diffusion happens from media to blogs in that data set, right? Media to media is the strongest, so other media pick from other media, which makes sense because half of articles we read kind of cites other articles in other media, their sister publications, and blog to media are rare, right? So if there is a blog, a media article like CNN or BBC picking up from that blog is very rare, right? So again, many extensions for this. It's a very fertile area of research. So you can have been extended to dynamic networks. So remember, here I learned just one network, right? How do you extend it to a set of networks if you have a set of cascades? Because the networks keep changing in real life, right? You can extend this to different cascade models. This kind of assumes silently that the model is like a cascade style model, but you can assume, you can extend this to more threshold style models and so on and so forth. Then theoretical analysis of how many samples do we need, right? To learn robustly the graph, right? So if I have how many cascades do I need, so I can robustly learn a graph with great certainty, right? So this is a very important theoretical problem. So people have kind of analyzed that too, and more accurate, efficient, and robust algorithms as well, right? So this general line of research has led to many papers. Okay, good. So I think I overshot by a few minutes, but the next thing would be viral marketing by Naren.
Yeah, is that okay? Okay, so we have two more questions left in this section, algorithms. So we'll talk about that and then go on to applications. So the first is viral marketing. Everybody knows about viral marketing. Aditya gave some good examples. The best example of viral marketing that we might be familiar with, that people talk about, is Hotmail. Apparently, every Hotmail account, every email sent from a Hotmail account had a little link at the bottom saying, have you tried Hotmail? Try it. And so essentially they were tapping into the underlying network, the word of mouth network, to do their marketing. So the question, the underlying problem in viral marketing is you have a limited budget for advertising your services or product. You have some notion of a network, you have some estimate of influence between individuals, and you want to market these products to the largest possible segment, and your goal is to try to target who are the most influential members to market to. And you're marketing to these members not because they themselves would purchase the product, but because they will influence or pressure others to purchase this product. So the influence maximization problem, formally stated, is that you have some influence function f of s, which basically says if you start with the seed set S, this is the expected number of individuals who would be influenced by that S, and you can apply this in different models. You can apply this like Aditya said in the independent cascade model. You can apply this in the linear threshold models, and the question is, given a limited budget K, determine who would be the set of K individuals who would maximize this f of S, and the problem is nphard. So we got to look for approximate solutions. This is a classical problem, which means that it's become old when people say classical, but everybody in this audience should know about this problem, because there have been 2 test of time awards for exactly this topic, and there have been 2 KDD innovation awards to the authors of these papers. So I'm going to completely skip this because we all know this. I'm kidding. So the basic idea in results coming from these 2 sets of papers is that under either of these 2 models, the influence function is submodular. So which means that you can start with a greedy algorithm. At each point, you can try to add the set of nodes that greedily optimizes this objective function, and you can prove that this type of greedy approach supports a very simple approximation, and a guarantee of performance. So the real problem that happens in applying this in practice is that the question of how do you actually evaluate f of s, how do you actually know the number of individuals that a particular seed set is going to influence, that turns out to be pretty difficult. So if you, the simplest way to do it is to do some sort of Monte Carlo sampling, is to do multiple runs under any of these cascade models to start from your seed set. So initially you start with your, let's see if this works. Yeah, so you start with your seed set. If this becomes your seed node, I can see it there but not here. And one run gives you, one run gives you these 2 nodes as being influenced, affected. Another run gives you these 2 nodes. A third run gives you these 3 nodes or 4 nodes, and you do a lot of iterations, do basically a Monte Carlo sampling, and you keep doing it till your estimation errors are small, but this gets prohibitively expensive. So a lot of the recent research has been on how do you evaluate it, what are good ways to approximate this, and these are 2 papers, one in NIPS 2014 and one in KDD 2015 last year. I'll just briefly talk about what their ideas are, and then we'll move on to the next topic. In one approach, you basically, instead of actually unrolling the whole graph and determining how the cascade will spread, you estimate neighborhood sizes and use these neighborhood sizes to estimate what the actual f of s function is going to be. In the second idea, you basically do the same Monte Carlo idea that I mentioned, but you use a map reduce K style approach to scale it up, and when you parallelize it, there are some interesting optimizations that you can adopt that will reduce the number of samples than if you do it naively. So that's about the viral marketing problem. Let me come to this problem that's actually a pretty interesting problem, and surprisingly has not been studied in the KDD community. Every paper we were able to find were outside of KDD. So if you're looking for a fertile topic, I think this is a great topic to do some research on, which is how do you pick sensors for graphs. So let me first explain what the problem is. Suppose you're trying to track an epidemic in a graph, and just like all epidemics, let's suppose it's going to rise up and then it's going to fall after some time. Can you define a subset of individuals who you can track, who would essentially become the sensor for the full epidemic, right? So if I say, for example, I'm just going to track these 5 people here, and if I track how they get infected, when they get infected, and so on, that's going to be a sensor into this whole room, okay? And who would those 5 people be? How will they actually design a sensor? And interestingly, there was this paper by Christakis and Fowler where they actually did this experiment with real people. Okay, so among all the papers mentioned here, this one is about a real social network. Okay, not Facebook or Twitter. I'm kidding. So this was a study done at Harvard. So what they did was they picked about 700 students, undergraduate students. Somebody joked that we know a lot about undergraduate students. We don't know anything about other people. So they picked these 700 or so undergraduate students over a semester, and they tracked when they got the flu, right? So they kept polling these people. Did you get the flu? Did you get the flu? Did you get the flu? So they have the full infection status of these people over a whole semester. And then they ask these people, who are your friends? Who are your friends, and so on. And they map the entire social contact network of these people. So from 700, they expanded that to 700 plus some 400 people to get the full network. And then they also took a random sample of students across Harvard. So they essentially had these two sets of students. So from the students, they got the friends, and then they have this random group. And they created a sensor network from that friend sample. So essentially, the friend sample is these 425 people. And interestingly, when they plotted this curve, let's look at the one on the right. You can't see this. Maybe I should use this. No. Okay. So if you look at the figure on the right, the red curve is the actual random population, the population that shows when the actual peak of the infection happens, and the blue curve is your sensor set. And you notice that the blue curve peak is shifted to the left of the red curve, right? Essentially, it provides you a lead time advantage into knowing when the epidemic is going to peak. So if you were to track just this subset of people and find out when they are getting infected, when they are not getting infected, that curve is shifted leftward, and the curve on the left basically shows the same, but in the cumulative form. And you can see that the blue curve is shifted leftward. So the idea of social network sensors is just this. Given a social network, find a subset of people that you want to track, determine their infection states, and use that to identify characteristics of the full epidemic when it spreads through the real network. So the main conclusion of this Christakis and Fowler paper was they spoke to the students, they asked the students to list their friends, and they picked the sensor network from that friend, and that turned out to be a very good sensor set. And this idea of picking friends is an illustration of what is called the majority illusion or paradox, depending on how you think of it. And the idea here is when people are asked to list their friends, they tend to list these high degree people first, right? So the flip side of this is that the minority, the people who might think they are in the minority, are actually give rise to a majority conclusion. So the example here basically shows a graph. In this case, these are people who like baseball caps or something, doesn't matter, or get infected, whatever. So the blue ones are the ones who like the baseball caps, and the other ones are those who don't like. But if you look at the network and you ask people, what about your friends? And let's make a decision based on your friends, you notice that the conclusion that you will come to is exactly the opposite of what the social network says. In the social network, you see only 3 people who like this baseball caps, but when you take everybody and find their neighbors and you make this majority conclusion, you're going to find that the conclusion basically says baseball caps is good. There have been some explanations that this type of phenomenon has been the reason for the shift in emphasis or support for same-sex marriage. When you ask people, why did you change your opinion from opposing same-sex marriage to supporting it, everybody says, I know someone who's gay, and that's the reason I tend to support it. So tapping into the social network and following that majority really plays a role here. So what people have done is, in addition to taking this type of social network sensor and tracking epidemics, they've also applied it on Twitter. So looking at Twitter and looking at messages where people post about some phenomenon, so in this case Hurricane Sandy, and trying to determine, can you find a subset of Twitter users, find out when they post about Hurricane Sandy, and use that as an indicator of the overall Twitter activity for that particular topic. And once again, they were able to get a little bit of a lead time advantage. You can see that the peak in one of these curves is shifted a little bit to the left from the other group. What we have done in our own work, this is joint work with Aditya and other groups, is we are trying to ask the question, can we try to design better social network sensors, better than this type of friend-of-friend approach. And the reason we started doing this was when we applied this on some of the real-world data sets, like the Portland data set that Aditya mentioned, we don't really get this type of lead time advantage. So one of the interesting things we found was that most of these sensor set papers were written by physicists, no offense, but they didn't quite formalize the problem. They were going about designing these sensor sets without really saying what these sensor sets were supposed to be doing, what problem they were going to be optimizing. So we spent some time defining the objective function of what a sensor set should be doing. So one way to do it is to basically say, I need a sensor set that maximizes this lead time. This turns out to be really intractable, so we dropped that like a wet towel. And then we started thinking about, can we try to find a sensor set that minimizes this average infection time. That turned out to be a more tractable way to do it. And one way in which we decided to approximate this was again using the idea of dominators. As you remember, we heard about dominators a few slides back. A node A dominates a node B if all paths to B have to go through A, right? Like I'm dominating your path from now to the coffee break, because without me stopping this, you're not going to go to the coffee break. So, so you're going to look at the notion of dominators in a complete network and use these dominators to form your sensor set. So that's what we did. We looked at dominators, and we found that using dominators and some other heuristics gives you a lead time advantage. But the real catch with dominators is that you need to know the full network. You need to know the complete network to realize that some node dominates some other node. So what we ended up doing was, being data miners, we asked the question, can we try to apply some machine learning on the dominator relationship? Can we try to find out what are characteristics of dominators so that we can apply that as a surrogate to determine what are good sensor sets? So we defined a classification problem where the target is to predict if something is a good dominator, and the features are all about demographic attributes. Is this what is the gender, what is the age group, what type of work does the person do, and so on. And we learned a simple regression or classification model using a CART methodology. And you notice on the right, you have two curves. One is the lead time using the dominator tree. The second is the lead time using a CART model. So essentially, you learn a model, and then you apply the model on the network, which will predict who are likely to be good social network sensors. And then you ask the question, is this going to do a good, what lead time you get with it? So, and you don't get as good a lead time with the surrogates, but you get a reasonable lead time. So this area is just starting. I think there are a lot of problems that can be formalized in the space of defining better social network sensors and tracking these sensors. And with that, I think we've come to our break. Any questions on this? Yes. So the goodness of a sensor is the lead time advantage, right? So the difference in time between your peak and the real peak. So well, it allows you to compare multiple sensors, right? Because if you come to me and say, here is a set, and I tell you here is my set, and you track both of them using a range of epidemiological parameters, whatever, right? Yours will be better if it gives a bigger lead time. Yes, correct. But that's what a sensor is. right? It's a set of individuals. So when we say a sensor here, it's a set of individuals who should be tracked as a prelude to the full, population. Yes. Yes. Correct. Yeah, essentially that's what we are trying to approximate, right? So that's what the dominated tree gives you, right? If this node dominates some other node, it means that the only way the epidemic can reach this set of people is through this node, right? So this better be a good sensor for that. But like you said, it depends on where the epidemic begins, right? If it begins in some other corner of the room, you should still have a good dominator for that. Any other questions? Okay, so we will take a really long break now.